The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So this is a nano-to-macro transfer process 2570 and for undergraduate students and 257 for graduate students. And it's offered every 2 years. So I'm glad to say this is probably the largest audience I've ever had. And so that's I'm very pleased to say the growing popularity. The last time we did OpenCourseWare, I think it was 2004. And that one, we had voice recording and typewritten notes. And you can still go to the MIT OpenCourseWare if you miss a lecture. I think although we do have changes, the changes are not dramatic. So you can go there and try to make it up if you miss any lectures. And this semester, MIT has a new initiative trying to put the course or video online. And so I volunteered. And also that way people can read my book better. It's a hard book to read. And in addition to my book, there are also a list of books recommended because you'll see that this course really covers a wide range of topics. So we have given list of references for each subject. You can always go to other books. This is not necessarily the easiest to understand, but to say we put it on reserve in the library. And with that, I think it's pretty much the housekeeping item done. And what I'm going to do next is to give you some slides. I'm not going to show slides every week, but I'm going to give you some slides to see what's the scope of this course and some motivational side. So any questions? If you look at the title, this is nano-to-macro transport process. So we'll emphasize the nano, we'll emphasize the transport, we're also emphasizing the transition from nano to macro. And so this is a slide from a colleague of mine before, and here what we're showing are the length scales that's in nature and length scales for what we make artificially. Right? Say nature, of course, we have the biological side, you can say, going to from molecules to DNA to bacterial cells and progressively increase in length scale. And then if we look at what people are making from, for example, those nanoparticles, sometimes we call it quantum dots, as small as a few 1, 2 to 5 nanometers, and to nanowires and nanoelectronics, where this is actually quite a few year old. I think the gate length in semiconductors now is just around few 10, 20 nanometers. So those are we're making smaller and smaller devices. And of course, at the end, what we're interfacing is at the macro scale. So when we go to small scales, the questions, because you have learned a lot in the transport theory, for example. The question is, are they valid or not, right? And what if they are not valid, what are the alternatives? And also, we're not just looking at the individual nanoparticles. When you put them together and into macro scale, what's the picture there? So this is where this course is trying to wrestle with, and that's in fact most of my research is looking into thinking how we can look at the small and then how using the small to do the big things. Particularly, most of the work I'm working on is heat transfer related to energy, and energy is a large scale. So how I can take small to go to the large. And let me give you two examples that from research to show that when you go to nanoscale, the classical theory that you have learned breaks down. And the first example is a heat conduction example, right? We know in heat conduction, we have Fourier law, and we have thermal conductivity of the materials. And this is one example of nano. This is, in fact, a transmission electron microscope image of a layer structure. One layer, the bright layer, is silicon. The darker layer is germanium. So each layer is about 2 nanometers. And then when you measure thermal conductivity, so you can take a silicon, because the one layer is silicon, the other is germanium, right? So you have started heat transfer. It's parallel plates. And then you can do thermal resistors to say what's the effective thermal conductivity. And you can say, if I take a silicon and germanium thermal conductivity, I will predict that's the equivalent thermal conductivity, those open circles. But the experimentally measured dots are order of magnitude smaller. And in fact, we have to go to a completely different theory. In this case, we have to go to Boltzmann equation to predict. Now, say this is the work that we started in the 90s, and now we're doing quantum calculations on those structures, right? So there's significant departure from the classical theory when you go to nanoscales. And as another example, you learned in thermal radiation, black body is the maximum of thermal radiation, right? But say when we go to nanoscale, when we put the two objects smaller, the distance, this was on MIT webpage. I really like this. They're very creative. Much as I say this is better than what we did. So that's a Planck's law, black body radiation. And that's usually considered maximum. And when we put two surfaces down to nanoscale, right here is 1 micron, 100 nanometer, and 10 nanometer. We can go beyond the Planck's law by several order of magnitude, right? When say this is a 3 order of magnitude, we're now at 4 order of magnitude, and we're looking at what happens between that 1 nanometer and contact. And you say, why you curious, right? The fact is, when I put many materials together, they say it's really, particularly when I do nano, it's really the interface dominates. And so that interface sometimes contact each other, sometimes they do not. So this is the connection, say how I can take this nanoscale and eventually go to macroscale. So this is a propaganda. I do nano. I say, once I was asked by graduate students to summarize research in 3 words, that's like what I came up, nano, heat, energy. And what I had benefited over the years is, I'm a mechanical engineer. I always say at the end, what I do want to be useful, right? So I think about atoms, but I also think about continuum. And I see we have few things we can proudly claim that we had really done some change in the materials. I gave an example on this thermal conductivity of silicon germanium superlattice, that layer structure. And we're taking that to make a better thermal electric energy converters, because we need the materials with the pool heat conduction, and we still need the electron go through. So this is a very contradictory requirement. And currently we're working on this photon side. We're designing nanostructure to do, using less material to do solar cells. And we have some of the most conductive liquid just by putting nanoparticles into liquid and find out what's the thermal conductivity. In fact, at the end we say, I don't want everything nano. That's where you understand, if you understand physics, not everything is nano also, right? So we work on people putting nanoparticle into liquid. Some say have high thermal conductivity. Others go to lab, they say, no, we can't measure it. We struggle for 4 years. and eventually figure out, we say, okay, eventually what we need is macro in one direction and nano in the other direction. And that's how we achieve the best thermal conductivity. And we also have the most conductive polymers. I get a call every month almost from the industry to say, can we have it? So the question was, polymers, plastics are typically poor heat conduction, right? So people always want to make them more conductive. Most people work is making them more electrically conductive. But say when we ask the question, I got a call from Intel, say, can you think about how I can better manage heat? I start thinking of plastics. So how I make them more conductive. And if you look at how people usually do it, they'll put in composite. They'll put in a larger component and make them average speaking higher heat conduction. And when I think about this, okay, of course that's approach, one of the approach. But see, the question we ask, is a molecule, a polymer, really a poor heat conductor? Is a molecular chain a poor heat conductor? If you think of polyethylene, which is 60% of the plastics, and it's a carbon-carbon bonding, right? And carbon-carbon, what's the highest thermal conductivity material? Anyone know? Diamond. Carbon-carbon bonding, right? So that suggests that in the molecular chain direction, I should have high heat thermal conductivity. Right? So you think about the nano, you think about molecules. And in fact, say, of course, I can put in more fancier theory. I go to Fermi, and he did work in the 50s. He said, one-dimensional conductor has infinite thermal conductivity. So that gave me a lot of motivation to look into that, and in turn, we did succeed in actually create the most conductive polymer, except it's in one single fiber, nanofiber. Right, so I say, I got a calls every month from a company. I said, you guys have to wait, or you give me money, we do more research, because I need to scale this up, right? Because you eventually are not using single nanofiber to put in your heat exchangers. So that's what I say. You need to think of nano. You have a lot of, you can generate more new ideas, but also you to think to how you can go to macro. And so this, when I say what's nano for energy, right? If you think about the energy, at the end it's molecules that you are mechanical engineer familiar with. It's the electrons, and it's a photon, the light, or it's lattice vibration, photon. Right? Those are the basic energy carrier. There are some other terms, but let's say those are the basic energy carriers, right? What's their characteristic length? The mean free path and the wavelength, right? So the mean free path of air molecule, will get into that very soon. In this room is about 100 nanometer. And that means they travel about 100 nanometer and they collide with another molecule. And the wavelength of light, visible light, how much? Wavelength. 400 nanometer to 700 nanometer range, right? So half micron. And so a lot of this in the nanometer range. And if you think about energy, fundamentally, if you can control the energy level a material has, for example, if I make a quantum dots that I showed before, 5 nanometer spheres, right? Particles. What happens is an electron, quantum mechanics say it's a wave, right? And a wave has a wavelength. And typical wavelength is, you can say, let's say, 10 nanometer. Now, a wave of 10 nanometer, you try to fit into that 5 nanometer quantum dot, what happens? You squeeze that wave, right? You squeeze that wave, the energy level will change. So if you look at Professor Munji Bowindi's homepage, you will see the quantum dots of different colors. That's because the energy level changed when you make the size change. So that's the one way you can control the energy. If you control the energy, now come to mechanical engineering or say any engineer, what do? You control the thermodynamics, right? Energy is the most fundamental. So you can control thermodynamics. And the other is, say, transport, right? If you look at where the losses are, if you say, okay, second law, color say you can get to color efficiency, pretty good. If you can get all color efficiency, you should all be pleased, right? But say we lose about 60% of useful energy if you look at the energy input, output. And color say you can get to 90%, right? So you can improve the transport if you can control the energy carrier traveling, their interaction, their traveling, right? So I said the air molecule is about 100 nanometers, the mean free path, and that seems to awfully small. But if you open your computer, you look at the hard disk, the separation between the disk itself, which is rotating about 10,000 RPM, and the magnetic head is a few nanometers in everybody's computer. So you go to this disk drive company, and they have give up the Newton because it's basically how to allow to crash that disk head with the disk, right? It's a fluid mechanics problem. And they have given up solving the Navier-Stokes equation because the fluid mechanics, that's solving Navier-Stokes equation. They don't use it for a long time ago, they've given up. And one day they call me, they say, we have 1 nanometer problem. I said, 1 nanometer? At the time, I didn't know even the separation. I said, why you care about it? Because at the time, they're about 20 nanometer separation. And they say that's already 5% uncertainty, right? And now they are going beyond, they are only, say, they are below 10 nanometers. We still didn't figure out what was that 1 nanometer problem, right? So, but there are a lot of, say, so basically, using the boundaries, and at this regime, you need to go to different laws. So what we're talking in this course and in this book are really, this is my view of trying to have a picture from nano to the continuum. And first, you need to understand the basic energy states, the energy levels in the material. So that really need quantum mechanics, solid states. And then I do heat transfers. I need to bring in the temperature. That's a statistics, thermal energy. And then we need to look at how those energy carrier moves. So that's the transport. In transport, you have continuum laws. You have also you need to go to long continuum. You need to vary whether you need to, say, in the quantum regime, where you have to look at the wave nature, or you can forget about it, right? So what I would like you to have is to develop that picture. Say, if you have a problem, and people come to you and say, well, in this regime, I'm worried whether I can still use the continuum, right? If you feel comfortable to tell them, yeah, there's no problem, just go. You may get a 10% error, 20% error. But say, at least say, I want to develop the comfort level of when you can use, say, what kind of transport pictures. And in fact, say, if you look at the book, it's a parallel treatment, say, of electrons, molecules, photons, phonons, right? So that's the way I understand the object, the subject. And I've been always a mechanical engineer. I first learned thermal radiation, photons, and of course I learned all those continuum theory. And it turns out that if you understand that one carrier, you can make a rather, it's easy, relatively easy analogy for other carriers. And at least in this so-called dilute gas picture, they are all the behavior are very similar. So this is what I'm most familiar with, and wave Maxwell equation. And but say this is where most engineers familiar with, right? Ohm's law, Fourier law, Newton's shear stress law, those are the continuum, right? But say if I go to photon radiation, where if you think about the photon from the sun to Earth, you don't go to solve diffusion equation for that. Right? In fact, let's say the simplest is just a straight trajectory, ballistic, right? So this is what happens if I have a disk drive. I have a disk, the example here. Average speaking, the molecule travel 100 nanometer, and now the molecule, if there is a molecule in the gap, they'll collide the wall. They don't collide with each other, right? That's the ballistic transport picture. So what I want to have is developing, say, when I need to think about the wave, when I need to think about the, forget about the wave, but say still need to say what's the boundary effects, and eventually say the continuum. So it's a very, the challenge for this is most of you, I know most of my students, they are mechanical engineers, right, with a mechanical engineering background. And that's where we're most familiar with, most comfortable with. And what we add to this is a lot of new subjects. And typically it takes many years to build up. But it took myself many years to build up. So I'm very ambitious to say, I want to teach you one semester. You will be inundated with terminology, okay? And also, but say what I'm hoping is at the end, you gain something. You gain that, say, you can look and say, I have a sense of from molecules to the continuum. So that's what we have in the general introduction. Any questions? I want you to feel free to ask questions. Before I turn off the computer, because I'll do that, say, every week, I actually will spend at the end of lecture 10 minutes or so to have some relaxation time, relaxing time. And what I want to show you is I don't know how many of you go to journals. And then most of you are graduate students. And you should go to journal every week, if not every day. And just look at what other people are doing. So when you are a new graduate student, you don't go to journal often, and you go to journal, you look at this, most of the stuff you don't understand. Other than the one, if you work on heat transfer, you go to journal heat transfer, maybe you know what the people are talking, right? So one might say if I want to start with any journal, not medical, not biomedical, I'm not familiar with that. Any other journal, you tell me. And I want to say, okay, where you are today and where you are at the end of the semester. And my ambition is for you to say, look at the paper title and 50%, you say, maybe I can take a look. Maybe I am not completely ignorant. So give me the name of a journal. Huh? Nature. Okay. Let's take a look. Right. So one of the challenge of Nature is that now most of them are actually biological, but that's fine. Let's say still say what's the news this week?
Social networks.
Huh?
There's one about social networks.
Social network. Social network. I want you to think about the entropy of social network. Right? I say, I tell you at the end I only need you if you in your career at the end you say, okay, there are only 3 words you need to understand, not just nano heat energy, right? There are only 3 words you need to understand: energy, momentum, and entropy. Okay. If you feel comfortable with that, let's look at the, say, where are the technical papers there? Research. Volcano. Those are the signs. This one I want to go more into the plasma, right? What is a plasma? And so when I look at this, right? Quantum coherent coupling of a mechanical oscillator to optical cavity mode. I look at that paper. I haven't read it, right? Clearly, I haven't. What I was thinking. Anybody will guess what they will be talking about? Huh? So you will say, I don't know. Okay. So my guess is it were probably related to force, momentum of photon. Right? It's a mechanical, and so it turns out that the photon has a momentum and it carry force. Once anything has a momentum, can generate force. So optical cavity. So you will learn those stuff. Okay. So the quantum control, I'm not very familiar, but say what I can say is the optical cavity, the modes, and also the coherence issue we'll talk not exactly related to photon, but related to transport, right? Say how I can go from that normally the wave are coherent state to eventually I can forget about the coherence of the waves and treat them as particles. So my point is say at the end, what I'm hoping is that you open journal like Applied Physics and Nano Letters or Science Literature, you're not scared. Okay, there are a lot of terminologies that you probably didn't know, and I'll stick to you and through to you, and maybe you remember something. Okay, so let's start talking more details. So what I want to start with is for you to think about what are the laws you have learned. Say, what are they? Okay, I want to get the. So we talked about briefly, let me just follow my syllabus. We show the slides on motivations, and scope. Now let's go to classical laws. Not necessarily classical. I just want to say what are the laws that you think you have learned. And particularly like transport, right? Okay, let's start with the conservation. So I'll use this side, right? We have conservation. What are the conservation laws? Huh? You have mass conservation. momentum what other? Energy. First law. Other. Charge. So charge on what? Charge transport? What? Oh, conservation of charge. Okay, yeah. That's. Huh? Parity. I'm not familiar with that. Okay, yeah, I heard the name. What others? We're not going to touch much on conservation laws. Einstein say that anything can be broken except the first and second law. So I'm not going to touch much on. Okay, we'll say okay, even though it's not a conservation, but the second law is say you can write the entropy generation, you can still write the equation there, right? So those are the things we don't touch much. There are discussions in literature say you can break the second law. That's in the time, very short time scale, and the statistical speaking, you could have deviations. That's possible. And let's look at transport. Tell me more on the transport laws you learn. So let's say you learn, some of you familiar with heat, some of you may be familiar with charge, or fluids, or mass, right? Tell me the laws in those disciplines. Huh? Okay, so let's do heat, right? Right? Heat in terms of the laws, the Fourier law is for heat conduction. So conduction right? This course I put a prerequisite at the 255 level, and 255 if from other department is basic heat conduction, heat transfer, thermal fluids course. And in your department, there's also a course, nano engineering. If you've taken that, this will be easier because there are a lot of there's some overlap. But say if not, you can still survive. So heat conduction, we have the simplest picture when one side is hot, the other side is cold, and there's a heat flow inside, right? And the law governing the heat conduction, I write the simplest form, is the Fourier law, right? Fourier law of heat conduction, the heat flux equals thermal conductivity times temperature gradient. And this is one dimension that I'm reading. And this is a heat flux. The unit here is a watt meter square. And the thermal conductivity is a material property at the macro scale. When you go to a nano, you'll find this is no longer material property because it's structure dependent. But the unit of that is watt per meter per Kelvin. And then we just said diamond is the most conductive, heat conductive material. And in fact, some people will say it's the carbon nanotube graphene. So this is at the nanoscale. On one side, it can go very high. On the other side, I give example, it can go very low. Right? So this is one of the laws, transport laws. And this is a conservation law. And for this law, what do we call? Constitutive relation. It's a relation between temperature and heat flux, right? And those constitutive relation, many of them have their regime of validity. And then you can, it's a law, you can break them, okay? And so since we're doing heat, what are the other heat laws? Okay, let's say convection. Right? So for convection, of course, for those who know Levi-Strauss equation, and you need to, this very complicated partial differential equations. But in the simplest picture, when we do convection, is I have a heated surface. Let's say this is a wall, and I have a fluid, and away from the wall, the fluid temperature is TA ambient. And then I write the law for cooling is Q equals H TW minus TA, right? This is the Newton's law of cooling, right? Newton's law of cooling. And H here is the heat transfer coefficient. The unit of H is different from K if you look at what we had for Fourier law, and it's watt meter square per Kelvin. H is not a material property. It depends on how fast is fluid, what fluid you use, right, and the geometry. So it's so for that you need to go to Levi-Strauss equation to solve if the case is simple. If the case is complicated, you go to do the experiment, right? And one thing I want to remind you, if you do fluids problem or heat transfer convection, on the wall you often invoke a condition. What is that condition? Low slip, right? So the molecule, the velocity of molecule is 0 or equal to the velocity of the wall, and temperature equal to temperature of the wall. That's the low slip boundary condition, and area of you learn fluids or heat transfer knows that. But I say that's not valid. That's not true. In fact, there's always slip. There's always velocity and temperature slip. It's just normally it's too small, so you can ignore it, and you will see why downstream. Okay? So conduction, convection. Radiation. Let's look at radiation. What's the radiation law? Okay, so let's write Stefan Boltzmann law. Q equals for black body sigma T force power, right? And the Stefan Boltzmann constant is 5.67 10 to the minus 8 watt meter square. And in this case, because it's not linear with temperature, so you have to use Kelvin force power. And I already commented before, we can go, if we go nano, we can go way beyond this. Okay? So those are the heat transfer laws. I'm more ambitious. I want to hear more. If you're an electrical engineer, you tell me, or chemical engineer, what are the transport laws? Or fluids. Right? These are the ones that I'm familiar with. Okay, drift diffusion. Let me simplify it further. Let's just write the Ohm's law. We'll derive drift diffusion. Okay, so here I have heat, and I will have a charge. And so Ohm's law. I want to write a differential form. So the differential form for Ohm's law is a current density. So here is a flux, right? Flux is a heat flux is a watt per meter square. And here current density is amp per meter square. Okay? Equals electric conductivity times the electric field. Right? Okay? So here I have amp meter square, And here I have inverse ohm per meter. But it doesn't look like a differential form, so I'm going to write it into a differential form. Electric field is the derivative of potential, right? So I have sigma and d phi dx. And I should have minus sign, right? So phi is electrostatic potential. Okay? So that's for charge, right? More. We talked about heat, we talked about charge. Fluid guy, tell me. Huh? Momentum, okay? Newton shear stress, no. Relate the force to the momentum, right? So Newton shear stress, no. Shear stress. And this is, again, if I take a simplest picture, if I have x, I have y. And in the fluids, there's shear stress, tau xy, right? And in the simplest form, tau xy equals mu du dy, where u, this is the velocity u, this is the velocity v. Right? So here we have dynamic viscosity. The shear stress is a Newton meter square, and the dynamic viscosity is then a Newton second meter square. Okay? So we have Newton shear stress now. And you can write it into more complex tensor form, 3D. I'm always writing the simplest one. What else? Mass. Tell me mass transport. Fixed law, right? Fixed law. So mass, we have heat, so we have mass diffusion. And the mass flux equals rho d and dc dx. Right? The mass flux here, you say, is a kilogram per meter square. Flux is always logarithm times meter square. And the diffusivity, Norris density, diffusivity is a meter square per second. And this, say, is the mass fraction. You can go to check the unit. Right? So we wrote all this constitutive equation. And in the first homework, you will derive it. So even though, say, in most of the classes, you're probably given, but you can use the simplest picture by counting the numbers. And if you have a gradient of velocity, you have gradient of temperature, you have gradient, say, in you have electric field, you'll see that this can be, when you go to see the granular picture, those nodes can be easily derived. And I'll show you in the next lecture how to derive them. Okay? So we said those are the continuum. Those are the ones at least you feel comfortable. And the question we ask is, when we go to nano, are those still valid? Right? If they are not valid, what alternatives we have? And to do that, we need to go to granular picture. We need to look at the individual charge, individual molecules, and individual photons. So what we are going to look at next, let's take a look at the simplest microscopic picture for this transport. Okay, so let's first look at we talk about heat. That's what I'm most familiar with, right? So let's first talk about the heat. And let's say heat conduction. So we draw this picture when one side is hot, the other side is cold. We see there is a heat flow. And now I want to look at the granular. Let's say I have a box with molecules. Let's say one side is hot, the other side is cold. Let's say we have gas molecules inside. How heat is actually conducted, right? I'm sorry? Gas molecule. So I take the simplest gas, there's no vibration. I take helium. Right, so this side is hotter, right? And the gas molecule, they do random motion. And at least, say when I say random motion, about half of them will go this way. And they will collide with the hot wall at higher temperature. And what they gain is they gain a higher kinetic energy because this is a higher temperature. When they bounce back, they have higher kinetic energy faster, right? So they gain energy when they collision, and they bounce back. The next molecule, they say, will have slightly lower energy, so it's the two-ball collision problem. And during that process, they'll pass some of the energy to the next molecule. And the next molecule, again, have different chance going this way and that way. And it's that diffusion process that heat goes from hot to the cold, right? So it's the random walk and diffusion process. And in fact, turns out, other than radiation, all those are similar process. Okay? And this is not an easy picture in the history of heat because way long time ago, people have this heat as their something calorie, right? Called when you have two objects touching each other, the calorie flow from one side to the other. So when you go to the supermarket, you still have the calories. It's a wrong concept we use the terminology today. Now, this is a gas molecule. What about metal? What carries heat in metal?
Electrons.
So electrons, right? So I put the metal, and what's the transport picture? One side is hot, the other side is cold. So that's the picture. So the electron now is the gas in the solid. They are bound by the ions, but they actually can move quite a few distance beyond. They are not just to say electron that these are free electrons. The electron actually can move around. And again, they will have a collision distance. Right? We said the air molecule collision distance is about 100 nanometer. And electron collision distance can be few nanometer to even longer, 100 nanometer, or even micron, depends on temperature. So this is amazing. There, millions of atoms. If you think of 1 micron, how many atoms there? And the electron can zip through them, and no collision. So, of course, at the end there is a collision. So if you think about that case, is the electron travel few distance and collide, and that's the same process. So it's the electron gas. We even give a name like a gas, right? So it's the electron gas. Okay. And next, what about a normal nonmetal? Diamond. Huh? It's a phonon. Okay. But most of you probably, the first time I heard of phonon, in fact, not the first time I heard phonon, but I remember when I was a graduate student walking into an electrical engineer, and they have an open house. They had an open house, the lab show. I said, I work on heat transfer. And the guy said, oh, you work on phonons. And most mechanical engineers, when they work heat transfer, they don't know what it was a phonon. Right? And a lot of you probably just graduate from undergraduate degree in mechanical engineering. How many of you have heard of phonon in heat transfer course? Right? Majority. Okay? So what is a phonon? I was teaching another university, and I had a colleague, and he said in my class, at the end, he said, I still don't know what is a phonon. Do you know what is a photon? Yes, sir.
Sorry, phonon?
Huh?
It's like a vibration through a lattice.
It is a vibration, yes. Yeah. It's not an electron. So let's say what is a nonmetal. Dielectric, let's first concentrate, right? So what holds the material together is the force, right? And if I think about two atoms in a material, and the potential between the two atoms, that's a typical curve, is like this. This is the separation between the two, and this is the potential energy. This is the minimum point. That's normally their separation distance, right? When they are further away, they attract each other, and when they're too close, they repulse each other because there is a charge in the. Every atom has a positive charge and negative charge. At the end, it's a charge that's the glue for the force, for the potential of any material. Okay, and so that's the force. That's the minimum distance, and of course the potential and the force is the gradient of potential, U. Okay, right? And at this minimum point, that first order gradient is 0. So I can write the potential, this first order, if I do the expansion, and I will write the force roughly, the potential expansion first order is 0, the second order give me a linear term. That's a spin. So the two atoms, the potential, the simplest approximation is a spring holding them together. Okay, so when I have a crystal like a diamond, it's a periodic arrangement of atoms. So they have their equilibrium position, and they are holding together by these springs. Right? So the spring, now you have this network, you look at it, it has vibration. And the vibration has a different frequency, right? So when we have vibration frequency, nu, and this is where it has to go to quantum mechanics. And it turns out that the vibrational energy cannot be arbitrary, and the energy has to be multiple of nh nu. The h is the Planck constant. 6.6, 10 to the, I only remember if you are a physicist, you will laugh at me. This is a h times joule times second, because physicists use atomic unit, they don't carry this large negative numbers. But I only remember the SI unit, so I carry that large numbers, a small number. Planck constant. H is Planck constant. So what this says is the basic energy is h nu. That's a quanta. That's the fundamental unit of the vibrational energy. And that fundamental unit is called a photon. It's not like an electron has a mass. But say it's very similar to photon. Photon don't have a mass. It turns out the photon has a frequency, and the fundamental unit again is h nu for photon. And in fact, later on you learn the Planck relation, is the energy is always related to frequency through h nu. Okay, so the photon is a quantized vibrational energy in the material. A photon is one quanta of that vibration. So if you do that, and going through, this is where you will have to wait probably until chapter 5, that it will go from the vibrational modes, it's a wave, right? We say, eventually I treat them as particles, and as a photon gas. So I go from that wave picture mode to a gas picture in the solid. So for the heat conduction, it's that photon gas in the solid. And once I think about the gas, it's the same picture. Right? When one side is hot, that photon gas lock at the wall, they gain higher energy, they go to next. So the photon mean free path, again, the collision between the photons, and turns out that it's a wide range. And we're doing quantum calculations on this. And some of them is 1 nanometer, others is 1 micron. Okay. So for heat conduction, that basic picture is this gas picture. That's why I'm treating photon, electron, and photon. At the end is a photon gas. And they just say the photon from the sun, when we treat it, is a photon gas, but they don't obey the diffusion laws like a Fourier law. They go ballistic. There's no scattering until they reach the Earth. Okay. So that's the conduction. Convection. What's the difference? Right? Microscopic picture for convection. Right? We say, okay, you have hot ore and the ambient. We gave the Newton law of cooling. Right? So what's the microscopic picture of convection? What's the difference from conduction?
Non-zero average momentum superimposed on.
Yeah, very good answer. So what in heat conduction is molecules are moving randomly, and they're moving at 300 meters per second, pretty fast. but their average velocity vector is 0, right? So for the conduction, we have the average velocity is 0, but for convection, this is not 0. Okay? And that could be 1 meter per second, 2 meter per second. But I said that molecules are always doing random motion 300 meter per second, much faster, right? But you know convection is more effective. That's because they are not a diffusion, because when they move from one place to another place, they carry all that energy directly from one place to another, right? That energy is enthalpy. So that's the fundamental difference. You still got those random motion. So when you go back to think about Levi-Strauss equation, you still have heat conduction term there. That random motion is there, yeah? But you got a convective term. Okay? So that's a convection. And in fact, if you take that, convection is almost the same as conduction, except rather than you just have a direct moving term. So I would say its fundamental is not too new a picture at this scale. And then we think about radiation, right? What's a thermal radiation? What's the radiation from a radio? What's the difference? Huh? So the radiation from the heat source is a photon. The radiation electromagnetic wave from radio source, we normally don't call it a photon, it's also a photon. It is all photon. And all photon in free space, you learn this at high school. Speed of light, wavelength, frequency, right? Which channel do you turn? What's the frequency? I turned to 90.5. But I forgot that's megahertz or kilohertz though. But it doesn't matter. Is it megahertz or kilohertz, I think, huh? Right? Anybody remember? I can't. So let me just put 100 kilohertz. I know there are 100 kilohertz range. And so what's the wavelength? Speed of light. 3, 10 to the 8th meter per second, right? So that gives me wavelength 10 to the 5th, 10 to the 8th, kilometer. Okay? So it's a photon, and the energy is h nu, that's a low energy photon. And it's generated by, you know that station, right? Oscillating current generate this electromagnetic wave. It's an oscillating current. So it's artificially you oscillate. What's the thermal radiation? Huh?
Distribution of all frequency.
It's a vibration of all frequency. That's the, what is that? It's okay. It is a cover a wide range of frequency, but it's still oscillating current. Don't say all radiation is a thermal motion, right? It's a thermally generated oscillating current. Then think about the atoms. Think about electrons. When electron move around, the general current, right? So it's the thermally random motion generated, and this is a much smaller oscillator, much faster. So if you think about wavelength, it's 0.5 micron, it's 0.5 10 to the minus 6. This is a 10 to the 14 then, right? Frequency is 10 to the 14, it's no longer 100 kilohertz. Okay? So that's the difference. But say in terms of propagation of thermal radiation, it's actually the same Maxwell equation. It's not different from what the electrical engineer does. It's the source that's different. Once they are out, the propagation, you write the same equation. Okay. So at the end, there are not many equations. And so that's the heat transfer. We can go other. We can pick up another subject here. Let's say charge, Ohm's law. Right? I want to show you easily how I can derive Ohm's law. And let's look at the charge. And of course, I do a lot of hand waving. And I have a conductor, electrons. I have a potential, right? What's the force on the electron? Anybody remember if I have a charge, I have a potential? Huh? If my potential is E, let's say this is the x direction, right? The force Fx equals charge times the field, right? So it's minus E times Ex. And this is what I really hate. The minus sign, I often get confused. OK, so I have force. And I'm going to write the Newton's second law, F equal ma. So this is m d Vx dt, right? F equal ma. And it turns out that what the electron does, we mentioned before, it collides, right? It can go certain distance, then it collides. So the acceleration time is between that collision. And collide, accelerate, collide, accelerate. So I'm going to give a hand waving. If I do that integration, I say that's tau. That's the average time between the collision. So my velocity then is, if I integrate this, right, I get E epsilon x divided by m times tau. This is the drift velocity. The electron at the end is sort of under this field is the movement average velocity of the charge. Okay? And now if I have this velocity, I can write the current, right? The current, what's current? Current is just the charge per unit time going across certain area. So if I look at the current, right, because Vx is the average velocity, so if I know the charge density per unit volume, then I write my J equals the current, right, is Jx is the charge that's in Coulomb times n and times Vx. That's my current density, right? If you look at the unit, E, anyone remember? Again, 1.6 10 to the minus 19 Coulomb. Okay, one charge. Again, I'm awkward. I remember SI unit. And here is 1 over meter cubic, because that's the charge density per unit volume. And then you do this is meter per second, and you get the here is a Coulomb per meter square per second. Coulomb per meter square is amp per meter square, right? That's your current density. So if I plug in there, what I have is E squared and tau m times n times epsilon x. That's Ohm's law, right? This is my electric conductivity. This is sigma epsilon x. Okay? Let's do another example. So I have heat, I have charge. I will now think about force. Let's think about the momentum, right? The pressure. Let's say we have heat, charge, momentum. Okay, what's the pressure? When you have a box of gas, you have pressure. What is that pressure?
Force the gas exerts over an area.
So is the gas. I have box, I have gas inside, I have molecules, right? They're moving. They're moving randomly. And the pressure is when the gas hit the wall, right? And they will change direction, bounce back. There's a momentum change. That momentum change gives you the force. So I can argue with you inside, I don't know what's the pressure. Now you stick your any meter there, you will measure that momentum change and you measure the pressure, right? Okay? So here is the, of course, the force, let's say, is Fx on the wall, is a single molecule, is Vx, this is larger than 0, mass mvx less than 0, divided by delta T. So that's the single molecule acting on the wall of force, right? Now I want to find the pressure in the chamber. I have a lot of molecules. Again, the density, molecular density n. And they are coming towards that wall and bounce back. So let me just make my simplest perfecting wall. So the coming velocity equals the bouncing back velocity. So it's a factor of 2. And I have a lot of molecules here. This molecular density is n. It's random, so half of them coming towards the wall. So my is 1/2 n. And in terms of the rate, the time comes to is still Vx. That's the rate. That's the rate coming. And this gives me the delta T I need. And then say I have 2mVx. I'm assuming, like I said, this Vx is just reflecting back. So this will give me pressure. Again, you go to check a unit. Okay? So what I get? I get this pressure equals n mvx squared. Right? Vx squared is the velocity component in x direction squared, so it's just 1/3, rough speaking, right? Homogenized, so it's just 1/3 of v squared. Okay, so what I have here is n m 1/3 v squared. Okay, now I want to show you ideal gas law. And v squared, and this is you have to go, you have to wait a little bit, but then let me give you, say, the equipartition, that's a statistical thermal, says here, equals mv squared, because it has 3 Vx, Vy, Vz, so each of these modes will give you this Boltzmann constant times T. So this one you wait. Statistical thermal, fundamental result, equipartition. Okay? So I plug in this. What I have, that 1/3 cancel, that's 3. 1/2 cancel, mv squared is kT, kBT. So what I have here is then is N kBT, and this is ideal gas law. It still doesn't look like ideal gas law, right? One more step. And one more step, I'll stop here. Okay. So N is the number of molecules per unit volume. So I multiply volume. So I have PV equals number of molecules times Boltzmann constant times T. Doesn't look like R yet. So I do N divided by NA, Avogadro constant, NA kBT. And this is your R. That's your universal gas constant. And this is your mole fraction. Mole fraction times R, universal gas constant, times T, PV equals nRT. Right? Ideal gas law. Hand-waving. I'm not doing it rigorously, of course. Okay? So, anyone remember knows KB? What's the number? Boltzmann constant? 1.38 10 to the minus 23 joule per Kelvin. Okay, so you go to look at Avogadro constant, right? 20 is 6.6. It's about 6 10 to 23. They cancel. 6 times 1.38 give you, right? That's the universal gas constant. Okay, so basically, where we're going is to look at those microscopic picture and look at the electrons, look at the photons, look at molecule photons, and count this N, count how many we have, count how much energy they have, and count how long they travel. And with that, you can do all the counting. So the whole thread line for the transport is counting the basic the microscopic carriers. And for that, we need to go in another more detail. Okay? So, any questions? We'll stop here. Oh, yeah. I sent a questionnaire. I would like you to fill it and hand back to me so that I can have some idea what's your background, what's your interest. Okay.